And welcome back to Human Physiology. So last time we talked about elements and atoms and subatomic particles, and we ended off on a discussion about valence electrons. So let's pick up there and start discussing how valence electrons dictate the chemical bonding behavior of an atom. So the first type of chemical bond that we're going to discuss is called an ionic bond, and thankfully there's a very easy way to kind of predict which types of atoms like to bond in this way. So for any chemical bond, this is going to involve a change in the number of valence electrons of the involved atoms. So this is why elements like neon and helium, which already have full valence shells, do not tend to participate in chemical reactions because it would spoil a good thing that they've already have. So this is what we were describing with the noble gases like helium and neon and argon and krypton and radon and things of that nature. But a lot of other atoms are going to not have full valence shells, so they're going to want to react in such a way that they somehow manage to pick up electrons or lose electrons or share electrons, some way of fulfilling the octet requirement. So for ionic bonding, this is going to involve an atom either gaining electrons or losing electrons such that it takes the easiest path towards filling its valence shell. So this is ionic bonding. So ionic bonding is going to be perfect in a case where you are trying to bond two or more atoms, and what you are proposing in terms of this atom gains electrons, this atom loses electrons, it should be mutually beneficial to everyone involved. So the example that we're going to use here is sodium and chlorine. So if we consider both sodium and chlorine, where they are starting in terms of how many valence electrons do they have, well, sodium has 11 total electrons. So 2 of them are going to go in the first energy level, so 11 minus 2, that leaves 9 left over. Okay, well, the second energy level can accept 8 electrons, so 9 minus 8 leaves 1 valence electron left over, and that is the 1 valence electron in its third energy level, which, because it is the outermost shell, is the valence shell. Well, chlorine has 17 electrons. Again, 2 of them go in the first energy level, that leaves 15 left over. Another 8 goes in the second energy level, leaving 7 remaining electrons that will go in the third energy level, meaning that chlorine has 7 valence electrons. Well, we can go ahead and draw up a very simple exchange here that should make everyone happy. So sodium has 1 valence electron. So think about it for a second. Would it be easier for sodium to lose the 1 valence electron that it has, taking it down to a total of 8 because that third energy level would disappear? Or would it be easier to somehow pick up 7 electrons to fill its third energy level? Well, it would be a lot easier for it to just get rid of the 1 electron it has rather than try to find 7 new ones, right? Same thing for chlorine. Would it be easier for it to gain 1 electron or get rid of the 7 that it has, right? So there should be pretty clear answers to both questions. So sodium is going to want to lose 1 electron, and chlorine is going to want to gain 1 electron. Well, if you consider that these 2 atoms are about to bond with each other, this seems mutually beneficial to both. So sodium wants to lose an electron and chlorine wants to gain 1. Well, what if we arrange so that sodium gives its electron to chlorine? That way, everyone ends up being happy. So this complete transfer of electrons from one atom to another, from sodium to chlorine in this particular example, is going to result in an ionic bond. Now, the disconnect here, the thing we have not discussed is, okay, well, we understand the whole valence electron deal, but what's the deal with the ionic bond? What is it about that transfer that now makes the atoms bind to one another? What actually attracts the sodium and the chlorine to one another? Well, let's go backwards a little bit and consider something else. So before that electron transfer occurred, so while sodium still had 1 valence electron and chlorine still had 7, each one of those atoms was what we would call electrically neutral, meaning that those atoms have an equal number of protons and electrons. It says neutrons here, that's a typo, but it should be electrons. So when an atom has an equal number of protons and electrons, that atom is going to be electrically neutral, meaning it has an equal number of positive charges and an equal number of negative charges. So its total charge should be 0. So you can imagine that if an atom willingly gains or loses electrons, this is going to have an effect on its electrical charge. It will take on a net negative charge depending on whether it gained electrons or lost electrons. So if we stick with the sodium and chlorine example, sodium, after it gave up its 1 valence electron, then has 11 protons and 10 electrons. So this means that it has 1 extra positive charge that is not balanced by a negative charge. So we would say it takes on a +1 electrical charge, and we would now call it a cation, or a positively charged ion. Chlorine, on the other hand, has gained an electron, so now it has 17 protons and 18 electrons. So it takes on a net -1 electrical charge, meaning it is now an anion, or a negatively charged ion. So an ionic bond in and of itself is the result of the electrical attraction between the cation and the anion. Sodium and chlorine bind together because sodium is positive and chloride is negative, and there is a natural kind of opposites attract thing going on here. So ionic compounds like sodium chloride, which you can see here, you can see at the bottom here how those sodium and chloride atoms kind of pack together and attract each other. So ionic compounds like sodium chloride, or potassium bromide, or magnesium fluoride, etc., these are called salts. So salts are going to be important to us later on because salts easily dissolve in water. So take some table salt and just dissolve it in some water, right? So it's easily dissolved. And this dissolution happens very easily because water has certain properties that we're going to be discussing a little bit later. So water's properties mean that it can break the ionic bonds and cause the ions to dissociate from each other and exist on their own in the aqueous solution. So when you have your table salt and it exists in solid crystalline form, that is actual sodium chloride. You actually have sodium and chloride atoms bound together. But when you dissolve that salt in water, you are breaking the salt up, meaning that now in the water what you have are individual sodium ions and individual chloride ions. They are no longer together. They are existing all on their own. So dissociated ions like this are called electrolytes when they are dissolved in solution, and they are called as such because they are capable of conducting electrical currents through bodily fluids. And as you can imagine, that will be extremely important later on when we start talking about the nervous system. So ionic bonding is going to be perfect for considering cases when atoms have a mutually beneficial arrangement, meaning that one atom has 1 or 2 valence electrons and the other atom has maybe 6 or 7. So 2 atoms that are already very, very close to attaining a full outer shell. But not every atom and not every bond is going to be like that. In fact, most of them are not. So as it says here, some atoms cannot satisfy the octet rule by forming ionic bonds. So if you try to use these 3 examples as your case studies, like 2 hydrogen atoms or 2 oxygen atoms, try to think of a way for these 2 atoms to completely transfer 1 electron or 2 electrons from one atom to the other. You cannot satisfy the octet requirements for both atoms by doing it that way. You can satisfy one of them, but you cannot satisfy both of them. And you cannot form a chemical bond if even one atom is not satisfied. So for cases like this, we are going to use covalent bonding instead. So covalent bonding is different because rather than completely transferring, completely gaining or losing electrons, we are sharing electrons. So we are spreading the love around. So what the sharing does, it almost seems like cheating almost, The sharing allows both atoms that are sharing the electrons to count those whole electrons towards their valence shell total, even though they're not really having complete possession of those electrons all the time. And electrons like this tend to be shared in pairs rather than one at a time. So a covalent bond can either contain 2 electrons or 4 electrons if it's a double bond, 6 electrons if it's a triple bond. So covalent bonding always comes in pairs of electrons. So covalent bonding can happen in 2 different ways, and it all has to do with the way the electrons are shared. In real life, when we share something, we can do it the same way. So imagine if I showed up to your house and I showed up with a cake. I'm not going to do that just to make sure nobody calls my dean or something and says, Dr. O'Mealy's going to show up to my house with a cake. No, it's not like that. So imagine fictitiously that I show up to your house with a cake and I say, hey, good news. I'm going to share this cake with you. So you would probably be right to be a little bit suspicious because you might be thinking, okay, are we going to actually split this thing 50-50? Are you going to get most of it and I'm going to get a little sliver? So you'd be right to be a little bit suspicious of me. So covalent bonding is the same way. 2 atoms can either share electrons equally or unequally. So if the electrons are shared equally between the 2 atoms, the resulting covalent bond is referred to as nonpolar, meaning the electrons being shared will spend exactly 50% of their time in the vicinity of one atom and the other 50% in the vicinity of the other atom. So in the case of hydrogen gas H2 up there, oxygen gas O2 there, or carbon dioxide gas CO2, which has 2 covalent bonds shown, the shared electrons between the involved atoms are spending exactly as much time around one atom as they are the other, meaning the sharing is exactly equal. Now, polar covalent bonds are a completely other story. So this is what happens when sharing is not equal. So if I show up to your house with a cake and say, hey, I'm going to share this with you, but I take 3/4 of the cake for myself, that's not very equal, right? I'm getting most of the cake and you're not getting nearly as much. So water is kind of our perfect case study in a molecule that shares electrons unequally. So the way to know when sharing is not going to happen equally is you have to consider for each atom involved something about it called its electron affinity, or sometimes called electronegativity. So electron affinity refers to, for an atom, how much does it really want electrons? So for something like, if we consider, say, sodium and chloride, sodium would have a very low electron affinity because it doesn't want to gain electrons. It doesn't want the electrons. It wants to get rid of its electrons. So it definitely does not have much of an electron affinity. Chlorine, on the other hand, because it is trying to gain an electron, has a very high electron affinity. So in cases where one atom has a ridiculously high electron affinity and the other has a ridiculously low electron affinity, that's a recipe for an ionic bond, and that's what we were discussing before. Now for covalent bonding, we're talking about 2 atoms that both want the electrons, one just happens to want it a little bit or a lot more. So in the case of water here, the 2 atoms are oxygen and hydrogen. Oxygen has a much higher electron affinity than does hydrogen. So when this central oxygen atom shares a pair of electrons with one hydrogen atom and shares a pair with the other hydrogen atoms, those pairs of electrons are spending a lot more time hovering around the oxygen atom than they are around the hydrogen atoms. And this is going to have a very important consequence. This is going to, because those electrons carry negative charges and because they're moving around and spending time around one atom or the other, this is going to cause the water molecule to take on what are called partial charges. So You'll notice on one side of the oxygen atom, we have these little lowercase Greek delta symbols with a negative by it. So that refers to a partial negative charge. And this is because that oxygen atom, because of its high electron affinity, because those negatively charged electrons are spending so much time around the oxygen atom, it takes on kind of a special negative charge. And then the hydrogen atoms, because they do not have as much access to those electrons, they take on what is called a partial positive charge, because the absence of the negative electrons de facto makes kind of a positive charge, because those hydrogens still have their protons. So water in and of itself is an electrically neutral molecule, but it is polar in the sense that part of the molecule takes on kind of a negative charge and part of it takes on kind of a positive charge. It's kind of like a magnet in that way. In the way that a magnet has a north pole and a south pole, water and other polar molecules like it have a negative pole and a positive pole. So this helps us to explain why it is that water can very easily dissolve salts and break their ionic bonds. Because for something like sodium, the sodium cation, which is positively charged, it can be very heavily attracted to the partial negative charges of the oxygen in the water molecule. Similarly, the negatively charged chlorine or chloride can be attracted to the partial positive charges in the hydrogen atoms of water. So water is going to have very special properties for us that we will discuss later that all really have to do with its heavy polarity. Chief among them is the ability of water to form what are called hydrogen bonds. Now, water is not the only molecule that can form hydrogen bonds, so things like ammonia, nitrogen is also an electronegative atom, so it is going to have chemistry very similar to water, but water is kind of the main one. So polar molecules like water and ammonia that have weakly positive hydrogen atoms are capable of forming these very special hydrogen bonds. So the issue with a hydrogen bond, and you can see in the picture given here that the hydrogen bond is just kind of a weak attractive force between the partial positive hydrogen and a partial negative somewhere else, whether it be on another water molecule or something else. A single hydrogen bond is actually very, very weak. It's not at all hard to break a single hydrogen bond. It's just not that strong. But the significance of hydrogen bonds is that hydrogen bonds do not occur in one at a time, right? So hydrogen bonds tend to occur in networks. So if you have a glass of water with almost countless numbers of water molecules contained within, well, each water molecule is forming several hydrogen bonds, somewhere between 2 and 4 each. So that gives even more total hydrogen bonds that are a part of a big network. So even though one hydrogen bond is very weak, cumulatively, they have a lot of strength, because if you're talking about functionally breaking hydrogen bonds, you're not talking about breaking just one, you're talking about breaking millions and billions and trillions and so on and so forth. And this will become very important because of water and its presence in bodily fluids. Hydrogen bonding occurs in nucleic acids to provide stability for things like DNA and RNA. Hydrogen bonding occurs to give proteins their shape. So we'll discuss all of these things towards the end of this particular chapter. So that is going to do it for our preliminary discussion on chemical bonding. Join us next time and we will start talking very briefly about chemical reactions. I will see you next time.